If you look at the history of computer standards, the thing about OCP, which is completely different, is that it's an ongoing innovation cycle.
We come together to innovate, to learn, share ideas.
The fact of actually having this incredible playground of technology here at a massive scale, which is super exciting as well.
We will continue to deliver systems at scale and to partner across our community to drive change. But we also want to work with you to seed the future of innovation, to identify those opportunities where one company cannot do it alone. As you join our community, as you flourish within our community, please show up, lean in, ask us questions, make contributions. This is our space. This is our time. Together, we can drive the future of computation. It's just open possibilities.
Please welcome Chief Executive Officer of the Open Compute Project, George Chaparian.
Good morning, everyone. I am super excited and honored to be here with you all this morning. We have a great show today, and there's those invisible hands here to make this happen. Thank you for being here. Our team today is empowering open, and we have selected this team to make sure that there are two major reasons. One is to celebrate and recognize all our community members in doing super amazing things. When I say community, I mean our members, our volunteer leaders, our supporters, and advocates throughout the world. You guys have done amazing things, like from air cooling to liquid cooling. From, let's say, modularized, inflexible designs to modularized designs, optics, and the list goes on and on. And the second reason is to make sure that this momentum continues with you and with the community as together collaborative with open and driving openness to make sure that all of us together drive the future with a lot of technological advancements. As far as the summit today, or this week, we have extended it for 3 days, as you know, to give you guys more extra day for engineering workshops. We heard you. We moved from day 0 to day 2 our Future Technology Symposium so that you can have more time to go there and evaluate, learn about all the new things and every great ideas that are coming together. We have 3 special tracks, and first one is the optical track, the CXL track of forum, and also the Sonic workshop. Please make sure that you attend those, and there's a lot of informative, good ideas that have come from those tracks. Those were, like I said, the hard work. The foundation team has been doing a great work for many months to come to this point, and there's a lot of invisible hands I would like to thank, and all of you here. Now to the fun part. During our reception today, Rebecca Wickley, our chairperson for OCP board member, with her team, they're gonna make a great, presentation in terms of their band, and we're gonna have some fun. Likewise, tomorrow there's OCP, Black Party that you should attend and also have fun. So let me talk about our foundation team. Here you would see faces that you know, and new faces that we hired. We asked Leslia to leave her post from a volunteer position to come in and be part of the team. She's driving the Future Technologies Symposium and Future Technologies Initiative. We also brought in Michael in a very critical time to make sure that the whole our business is seamlessly continuous, and also helping you all from the community to make sure that the partnership is alive. We heard you. You told us that our internal processes should be more efficient, our operations should be more efficient, modernized, our IT, our infrastructure, and the tools. And most importantly, to do easy business with us and more easy in terms of easier to come in, easier to collaborate, onboard our new members, and also all the contributions that you brought in to make it more efficient. So we brought in Kevin. Kevin is going to link our external, internal systems, and he's going to be very busy. We hired Bijan as our new CTO. Bijan comes in with tremendous knowledge and skill set from data center to telco to mobility, Wi-Fi, and also software, which we believe OCP should start moving to that vision as well. And we have an opening. It's a community technical program project management position, very exciting role to work with the community in terms of all the specifications and all the contributions and supporting Michael and also Bijan. Let me take a moment here to pause and recognize Bill Carter. Bill has been with the foundation almost 7 years plus, and he has done with the board and the foundation team amazing things to bring OCP to this level. Thank you, Bill. And I'm also happy to report that Bill is staying with us as a fellow OCP Emirate to help me and also help the foundation. Now, moving on, what you are going to see today, what are we going to reveal? We've been working for the foundation team, with the board, we've been working for, and you guys, of course, for almost a year and a half, 2 years, and we're going to reveal that we are going to bring our new tenant into OCP and our also top level project. We are working closely with our sister, or call it, open source communities, foundations, and we're strengthening our partnership with them, especially for making sure that collectively the system, as a system, comes together. And you will hear a lot about our endeavors in that area. We are seeding the market, especially emerging. We're trying to outreach globally to go places. And this is where we have re-engineered or redesigned our programs. And you can hear about a lot of new contributions today. So I encourage you to be on the floor, to talk to people and collaborate and network to get all these benefits. Moving on, looking at the year, beginning to date, we have successes to celebrate. Of course, without the vainglory, with you, without the community, we cannot be here. Every year, we ask AMDIA, a market research organization, to go and do research for us in terms of market impact, OCP market impact. When we say OCP market impact, we mean how our OCP gear, standard gear, our solutions are being deployed and adopted out there in the marketplace and globally. I'm happy to report that in 2021, as you can see, OCP impact, the market impact was 18 billion. And they predict 5 years from now is going to be 36 billion. And this is, without vainglory, remarkable for a small organization such as OCP driving this kind of impact, influence in the market. When I say small, foundation is small, our board of directors are small, but small in numbers. But with all of you, with the community, we're big. We are achieving almost 300 members now. We have 5,000 participants, active participants. And our annual attendees for these events such as this, measures about 4,000 people. I'm very happy to report that today we are approaching about 3,500. That in the beginning of the year, we thought it's not going to be possible because of all the economic conditions and world affairs. This is great. Thank you for being here. Thank you for supporting us. And virtually, the 10,000 people view these events. We have 2,080 plus contributions, about 140 marketplace SKUs today, and about 12,000 hits per month about all these, how going on there and looking at how the solutions are being formed from all the members and also companies that are putting together modularized solutions, standard solutions. We also have about 8 OCP-ready co-location facilities in the world and about 11 global OCP experience centers. I will explain later what we're doing to outreach globally and move those OCP experience centers, worldwide. Of course, from a social media followers, we're averaging about 40,000 plus. Now, let me explain what we're doing in terms of redesigning or bringing new projects and programs for our outreach, global outreach. This is called OCP Experience Center. We're doing it with our partners, with our members in all regions of the world. And today, I'm happy to announce that we have 11 of them already in place. These are showcases. These are like, executive briefing centers, if you may. These are, our partners, our members voluntarily working with us, taking OCP brand name, but with their solutions, showcasing on their premises, devoting floor space, devoting the solutions they have put together to solve the problems, and making a showcase in terms of how OCP and the partners come together to solve, far-reaching technological problems and also advancement. And I'm happy to report that there are 8 of them now currently work in progress. And here you can see all our partners that have devoted their time with us, their floor space, their engineers, and so forth to help us with OCP, with the brand name of OCP out there to really perpetuate what the value proposition of OCP out there. And today, I'm happy also to report it happened that it coincided with our summit that ARM finished their convergence of their experience center, and they're going to announce it. So thank you all partners in participating and helping us for taking our message globally. And this is really exciting. All right, so you, the community, and all our partners, again, I cannot thank you enough of how you're driving, critical thought leadership. Because of that, in 2019, we launched this program called Future Technology Symposium, basically looking at identifying emerging technologies, ideas, and cultivating them, incubating them. And I'm happy to report that today, from 2019 to date, we started with 20. We have now 300 participants. We have from 14 to 16 submissions. Really appreciate your partnership here in making this happen. And because of this, we have selected 2 awards, $10,000 each, for members that are really in this category of getting this award and making the investments for their taking those ideas into fruition. Because of the successful launch of Technological Symposium, we have also launched now another program called Future Technology Initiative. This is where we bring all these ideas together, and with R&D, with startups, with our community, with the networking, making sure that it's accelerated and into development, into project state. So I'm happy to report today that we have graduated the first workstream transition. This is the software-defined memory. And also launching computational storage and many, many other new work streams in 2023. Please make sure you attend tomorrow the symposium so that you can learn about all these emerging ideas and how you can participate and collaborate with us. Now today, we have very dedicated and esteemed colleagues from the industry as keynote speakers, and also from our board members. I'm very honored and it's a privilege to really work with them and bring this summit to this kind of caliber. They're going to talk about the vision for the data center, how to bring silicon, memory, hardware, software accelerators to make sure that the complex workloads are being managed, especially for AI, ML. And as we have seen, and we all know that Moore's law is getting to that level of pushing the threshold of elasticity of breaking. So it's really evident that if you bring network and distributed systems together, you can augment Moore's law even to take it further and continual. And finally, we would like to do all these in a very sustainable manner, and you will hear about sustainability, projects, initiatives that we're embarking to make sure that we help the planet in terms of recycling, reuse, and etc. So with this, again, I would like to thank you on behalf of the foundation team, the invisible hands, the people that put this great show together, the other invisible hands, and also our board of directors for being here. Thank you very much. I wish you great 3 days. I'm so excited to get to know you all and get out there, and also together, collectively, again, with empowering open, making sure that we push the envelope of technology forward, and together we kind of divine and decide how we're going to predict the future. Thank you very much.
Please welcome Intel's Corporate Vice President and General Manager, Data Platforms Engineering and Architecture Group, Zane Ball.
Good morning. Good morning, OCP. It's great to be here. I just wanted to start by thanking OCP and thanking all of you. I feel like OCP has really become the premier venue and organization where we come together to advance at-scale computing. And I think we have a great deal of work in front of us, and that's mostly what I wanted to talk about today. So if we want to contemplate for a moment the future of at-scale computing, data centers, cloud computing, I think 3 words come to mind. The first is scalable. I think we have succeeded in creating a world where our users can imagine that computing is this infinite resource, infinitely scalable that they can access at any time. Of course, we know it's not infinite, and it's a great deal of work to make that illusion happen. And in the future, we're going to have to double it in the next 3 to 5 years, and then we're going to have to double it yet again. And how do we do that while making sure everything is sustainable? And the final word is security, but I didn't put it on the foil because I'm not going to talk about it today. These challenges are really immense and kind of scary when we think about it, but I think it's useful to look at what we've accomplished in the past. We have an amazing track record in this industry of delivering energy efficiency, of delivering more compute for less energy. And a recent study in Science magazine showed that from the period from 2010 to 2018, we reduced the energy intensity of data centers worldwide by 20% each and every year. That's an astounding accomplishment. That means we increased compute instances by 550% while only growing electricity consumption by 6%. It's sort of mind-blowing. And I think it's illustrative to think about how we did that so that we can chart a course for how we can continue in the future. And the first piece of it is, of course, Moore's Law. We've been able to build more efficient computers. We've been able to deliver more performance per watt, per dollar. A compute node today delivering the same amount of compute as 2010, is less than a quarter of the energy consumption. But that alone was not enough to deliver those kind of results. We had to invest in very large-scale computing. The shift to hyperscale introduced tremendous efficiencies, according to these researchers. And what's also exciting, and I noticed at last year's summit, was that technologies pioneered at the hyperscale are diffusing out into the edge and the smaller deployments. So the innovations that happen at hyperscale have an impact even beyond. And then finally, according to this article, the rise of virtualization revolutionized the efficiency of data centers by allocating hardware more efficiently than ever. And I think the key point there is that hardware and software working together accomplishes a great deal. So if we think about this amazing journey we've been on, I think it points us directly to the future that we need to pursue. First and foremost, we need to continue with Moore's Law. And I'm not going to talk to you about EUV and ribbon FETs and that sort of thing, but I think as an industry, we have to work together to unleash Moore's Law. Second, hyperscale efficiency. We can't be satisfied with what we've accomplished already. And I'm going to point out a couple of technologies that I think point the way to some significant gains in the future. And then finally, inspired by the progress from virtualization, hardware-aware software and software-hardware collaboration generally is going to yield outsized gains that are really going to drive the future. So anyway, I'm going to talk about each of these in turn. So let's start with Moore's Law. Not surprising that the Intel guy is going to talk about Moore's Law. So we know that increased scaling in semiconductors is going to give us more performance per watt. But it's becoming increasingly challenging for systems to take advantage of it. And that's the piece that I think we together have to work on. If we think of what the system has to do to realize Moore's law, there's really kind of 4 things. The first is I/O and memory bandwidth. And here we've made a great deal of progress. We have DDR5 hitting the market, and DDR5 is scaling really well. So memory bandwidth has moved forward well. We have PCI Express Gen 5, which is scaling I/O. We have new technologies like CXL, which bring coherency to I/O and give us a lot of tools to create innovative, composable systems, expand memory, do those sort of things. So that part I feel very good about. We also have to bring power into the machine. I also feel like we've made a great deal of innovations into powering these semiconductors. And then finally, we have to make innovations in cooling them, because today we're sort of reaching the limits of cooling, and I'm going to talk about that a bit later. And then finally, one of the biggest barriers to taking full advantage of Moore's law is resiliency and the blast radius that a system has for the overall operation. If you go from 128 core systems to 512 or 1,000, just looking out over the next several years, how do we make that reliable? How do we make it such that software and hardware can deliver mission-critical results? That's a real challenge. And one of the areas that is going to be talked about a lot in the next year is component resilience. And it's an area we've been investing in heavily at Intel, and we're proud to be working with OCP on the new server component resilience workstream with a bunch of our key partners here at OCP, including Google. We have done a lot up until now in terms of silicon architecture, in terms of silicon testing, in terms of system-level testing, and we've also realized that you need fleet-level testing throughout the life of semiconductors in order to assure the level of resilient operation that these new systems demand. But when we look into the future, we see that that's not enough, and that's the important role of this work stream. I believe that software and hardware are going to have to collaborate together to provide the level of resiliency and the level of reliability that these new large-scale systems of the future are going to require. And I'm looking forward to the panel discussion on Thursday, where we're going to dive into this in more detail. I'm sure it'll be exciting. Second, how do we expand the gains we've made with hyperscale? I believe there's 2 key technologies. There's probably actually 10, but there's 2 that I'm going to talk about. And the first is modularity. The way we design servers is undergoing a revolution, and the way we've done it in the past is simply not going to be sufficient for the future, either from a sustainability point of view or a scalability point of view. And the way we cool systems with air is running out of steam, and I think we need to embrace the radical step of immersion cooling. Neither of these things are going to happen on their own. They're going to require OCP, and they're going to require companies in this industry to come together and drive change. So I first wanted to talk about modularity. So I'm super excited to see that OCP is leading here with the DCMHS, the Data Center Modular Hardware System. So HP, AMD, Dell, Google, Meta, Microsoft, and Intel have all worked on this specification, and it's become increasingly mature. And what modularity does for us is it allows us to reuse components, which is very sustainable. It allows us to engage in a circular supply chain. It allows us to optimize PCBs, which are the #1 contributor to the embodied carbon of the server. So there's a bunch of sustainability values. But it also allows us to save R&D costs and bring new systems to market faster. Because once we've validated the individual building blocks, we can literally build dozens of servers based on the same robust component. So to better illustrate that, I've got a video to show you what DCMHS is all about. So let's roll the video. Thank you. It's a really exciting vision, but I really want to make the point that it's not vision. It's here. This is our 4th gen Xeon scalable processor based dual socket, full width DCMHS reference design. So this is available for development today. And we also have a density optimized offering that I have here. And then our partners at Jabil with Intel have developed a full-on density optimized server, the Mustang. This is going to be in production in 2023. So it's reality. I believe that DCMHS is going to be rapidly adopted by the industry because it offers so much. And the collaboration between these companies has assured that this specification is robust to the needs of the industry. You can use it to build edge servers. You can build it an enterprise server or a cloud server. And I/O can be on the front. I/O can be on the back. What used to be unique designs are now built from the same building blocks. There are 6 specifications, hundreds of pages of technical details. I believe it's ready to go and ramp. So we've been working hard on that. But let's talk about cooling. So air cooling has been with us for a long time, and people have talked about liquid cooling for a long time, and it's always that thing we're going to do in the future. I believe we've reached a time where liquid cooling has to play a much bigger role in the data center, if for no other reason than the PUE capability that liquid cooling brings. And if you're in a humid climate, the numbers here don't even begin to scratch the surface, right? Evaporative cooling is really challenged in some of those climates. But the PUE of 1.03 doesn't even begin to scratch the surface of the value. Once we've moved, especially to immersion cooling, we can take the fans completely out of the system. Fan power is a major contributor to overall data center energy consumption. And let's not forget about the water consumption. In North America alone, data centers consume hundreds of millions of gallons of water per year. And all of that can go away. So it's a much more sustainable capability. So why haven't we already been there? Well, because it's kind of hard. There's a lot of problems to solve. The cost of entry are too high. And though a bunch of companies, from very large ones to innovative startups, are joining this ecosystem to solve those problems, we still have work to do. I believe there's been more energy around immersion cooling in the last year than I've ever heard in a very long time, and I think the time is now. One of the problems that we need to solve, however, are the liquids themselves. So the liquids touch every component. Every component somehow needs to be qualified to work with the liquid, and it's a problem. So we need to standardize the liquids so that systems know what to expect from their liquid. Intel's leading here. We are bringing out a specification with partners through OCP, and we are eager to engage in the rest of the industry to make liquid standardization happen so that we can scale immersion cooling. There's other problems we need to solve too, but this is foundational. Because of our ability to get a good liquid ecosystem going, Intel is going to be able to now offer warranties on our components with immersion cooling, which is a big step forward. So I'm really excited about it. We're ready to go on immersion cooling. But that's not all. Finally, and I think the most important task for the future is getting to hardware-aware software. I don't know about how you guys feel, but I feel like sometimes the software developers and the hardware developers are on different planets. But the actuality is we're on the same planet, and we've got to be responsive to the needs of this planet. And hardware is not the only important thing when it comes to driving energy efficiency. And yes, we can leverage Moore's law, and we can get 10, 15% improvements in energy efficiency. But if hardware and software partner together, we can get massive gains. I believe that there's a 10x opportunity if hardware and software work together. And there's a lot of ways to pursue, including continuing to improve virtualization. But the one that I wanted to focus on here today is workload acceleration. And certainly, I'm not the first person to bring up workload acceleration, and many large companies have leveraged it in specific cases, but we've struggled to scale it. And I think we have to have new energy behind bringing software and hardware together. Now, in our upcoming product, the 4th generation Xeon Scalable processor, we've invested a lot in accelerators, and these are some examples of what we can do. For example, encryption, which is already accelerated, we are accelerating it further with 4.2x gains. Data compression, up to 2x gains. Inference, one of the biggest workloads worldwide, we can accelerate up to 30x. This is a big deal. And if we work together, we can make it happen. But I think the mechanisms that we have with the hardware living on one planet and software living on another planet isn't getting us there fast enough. Accelerated computing is responsible computing. And we really have to start thinking of it that way. When we check in software into open source projects, we need to understand the carbon footprint that we're creating. And when we're designing accelerators and hardware, we need to understand how we plug into that software community that's going to use it so we can actually realize these kinds of benefits. We've done it before, we can do it again. So really, I think the key message is we have enormous opportunities to drive efficiency in the data center. Most of those align well with our economic goals of bringing TCO down and performance up. But to really get the gains and to scale them fast enough for what the world needs, we have to really work together. So we have to continue with Moore's Law, and we're going to keep working on that at Intel. But we have to build systems that can take advantage of those benefits. We have to continue hyperscale. We have to deliver on modularity so that we can deliver the benefits that it brings. We have to manage this transition to liquid cooling, which I think is going to be tough. But when I talk to people in the industry, some people say we're ready to go now. Some people say it's going to take 3 to 5 years. But I don't hear anybody saying that we don't have to do it. So I'm super excited about that opportunity. And then finally, hardware and software working together. I would challenge you and OCP to help us find the way. And with that, thanks and enjoy the show.
A friend of mine told me about the table tennis on the Quest. Okay, let's play. Okay. You can play with anybody in the world. That changed everything for me. All right, all right. I don't feel I have Parkinson when I play. I'm free completely. Woo! When I was diagnosed with Parkinson, I would stumble. So a friend of mine invited me to play table tennis. Cool. And I felt the next day much better. If it helped me, it could help other people. So that was the whole premises of organizing Ping Pong Parkinson. No mercy. Okay. We are competitive. You wouldn't believe it.
Please welcome Meta's Vice President of Engineering, Alexis Bjorlin.
Good morning, and welcome to the OCP Global Summit. I hope that video that we just watched moved you the way that it moved me when I saw that. So that's really a testament to Meta and what we're trying to do to bring people together in the communities. Similar to this OCP Global Summit has been a community that's been together for over a decade. So our mission at Meta is to give people the power to build community and bring the world closer together. So as you know, Meta's been a huge supporter of the Open Compute project since its very beginning. We've made countless contributions, and the same will be true today. This year's no different. So in a moment, I'm going to be updating you on some of the critical work we've been doing as we continue our march towards bringing AI at scale. But first, I want to share with you what scale looks like at Meta, since it's continually evolving. At Meta, the scale of our community has grown. Across our family of products and apps, we touch nearly half the world's population on one of our services every month. And as we build towards the metaverse, we now have over 750 million users using AR across our platforms on a monthly basis. These interactions are dynamic and global, and they require a massive infrastructure to support it. To give you just a sense of that scale, we have over 14 live data center regions, which has over 20 million square feet of active footprint, and is powered by and supported by 100% renewable energy. So increasingly, though, our whole infrastructure is centered around AI. So AI powers everything that we do. Most notably, AI powers what we're doing with content understanding. As an example, AI can detect and take down 95% of objectionable content before it even reaches the user. In Q2 alone, our AI systems removed nearly 250 million pieces of content violating our platform security across just Facebook and Instagram alone. So content understanding relies on multiple models that run beneath it: computer vision, natural language processing, and other models. We also use AI to recommend 15% of content in a person's Facebook feed. We do over 25 billion translations per day on Facebook and Instagram. And perhaps the coolest stat up here is that we do 90 million model predictions per second on our services, in particular on our Instagram Explore page. So as models go, one thing that we've shared very openly in the past is our deep learning recommendation models, our personalization models, or DLRMs. These models are truly massive. So they're on the order of tens of trillions of parameters today, and they require over a zettaflop of compute. So these DLRMs, they have a huge tax on our infrastructure in unique ways. And if you look at the two graphs behind me, one showing the size of the model and the other showing the compute required to train the model, you'll see that even though our models are among the largest in the world, they don't require the largest amount of compute, DLRMs in particular. So this is actually because we have both continuous and categorical data features that we save in very large embedding tables. So this type of recommendation and personalization model requires a mix of model parallelism and data parallelism to train. So the bottom line, and for our AI systems, we really need to pay close attention to the balance between compute, network, and memory bandwidth in the AI systems as we build the largest scaled-out clusters in the world. So let's talk about the AI systems we're building. As I mentioned, AI is a huge focus area for Meta, and we've been investing very aggressively to stay ahead of the leading-edge AI compute platforms. As with other technologies, we've been diligently bringing these platforms to the OCP open community. And today, I'm really excited to announce our newest addition to our AI family, our follow-on to the Xeon system, Grand Teton. Grand Teton is Meta's next-generation AI platform. As compared to Xeon EX, which you're maybe familiar with, it's been enhanced to support better network and memory-bound workloads, such as our DLRMs, as well as compute-bound workloads, such as content understanding. We've done this by expanding both the memory and network bandwidth and the operational compute envelope. So this system has 4 times more memory to locally store and run larger models. We have 2 times greater network bandwidth to enable scaling of the sizes of the clusters. And Grand Teton offers significantly greater compute capacity to enable next-gen models with larger numbers of parameters and even increased complexity. So unlike the previous generations of AI platforms, Grand Teton is a single monolithic system design with fully integrated power, compute, fabric interfaces, and control. This high degree of integration dramatically simplifies the deployment of the systems to install and provision in the fleet, and also reduce potential reliability points of failure down the line. So with the rapid scale and increased performance and reliability, that's what Grand Teton offers. We're excited to showcase this newest member here at the summit, and I really would ask you all to consider going to the booth where you can test out the system in full VR and AR using the systems that we have in place there. It's really pretty cool. Now, with the introduction of this newest AI platform, we've determined it's also a good time to rethink the rack. We need increased power. We need increased thermal capabilities. ORv2 has served us for the better part of a decade. But with these higher power platforms and the eventual need for liquid cooling, as we also heard Zane just talk about, we need to reimagine the rack for the future. So with that, I'm also pleased to announce our 3rd generation open rack called ORv3. ORv3 provides flexibility. It's got a 48-volt power system where we can accommodate both larger power and total power needs, but also the power transients. So we have flexibility to support OpenU as well as 19-inch RU gear. We can future-proof this with the ability to support a diverse array of cooling options as we increase the rack power envelope as the need arises. So the other really interesting thing here is we've reduced the total number of component counts from 160 down to 14 for a single power shelf config. The AI and accelerator and general compute roadmaps that we're also interested in, they're continuing to push the limits in performance and in also per socket power supply. Today, we're already deploying per socket power consumption of 400 to 700 watts, and with a clear path to a kilowatt in the future on the short-term horizon. So with this increased power comes increased transients. The Grand Teton design and the ORV3, this whole rack can also support 300% power transients. Modular power shelves also on the designs also add in additional shelves to support these higher peak power loads just about anywhere on the rack. But as we know, with higher power comes more complex thermal management. ORV3 has been designed to accommodate multiple future modes of cooling, including the short-term air-assisted liquid cooling, as well as facility power cooling. From this graphic, you can see what the facility water cooling we could comfortably manage, out to about a kilowatt per socket, and that should last us at least a little while. So this is an area we can all collaborate, working together to align on liquid cooling standards around connectors and normalized temperatures would serve the community really well. So like Grand Teton, we're excited to showcase this newest family member in our booth, and we're preparing to contribute the no ORV3 rack design to OCP in the coming months. This theme this year of empowering open for OCP is something that we're deeply aligned with at Meta. And it applies to more than the hardware. It applies to the software as well. So we've been at the leading edge and empowering an open community around PyTorch for a long time. PyTorch is our language of AI within Meta. And increasingly, it's becoming the language of AI across a much broader community. So in addition to the progress that we've made on the technical governance side, last month we transitioned PyTorch out into the PyTorch Foundation, together with AMD, AWS, Google, Microsoft, and NVIDIA, to form its governing board. We're really excited about this, and it's very similar to some of the messages that Zane was giving, because one of our top goals is developer efficiency. So we really believe in software-defined hardware, and we believe that the tighter hardware-software co-design that can be enabled from the model through the PyTorch stack, down through the compiler, and down to the systems and the silicon itself is what's going to enable us the leanest, overarching system design and performance that's going to be required to power AI in the future. So what do we focus on next? As you all know, Meta has been driving progress in networking for many years. Wedges, 6-packs, mini-packs, optics. I've often sat in the audience and have watched these be unveiled. We're pleased with the entire community's willingness to support and embrace these designs. But the fact is that the network and the memory bandwidth is still lagging that of compute. One of the challenges we face is that the interconnect hasn't been advancing at the same pace as compute in modern systems. On the silicon level, the commercial GPUs, CPUs, even domain-specific accelerators have tended to focus on the heaviest compute with relatively modest networking and bandwidth. This actually, when you look at what we've shared on our DLRM models, it doesn't match the needs of our workloads. So there's a lot of important innovation that's going on in modern HBM architectures and CXL memory expansion to increase speed and capacity on the memory side, but the gap still remains in both the memory and the network. This is one example behind me of the exposed time spent in the network. That's the amount of time that our compute can be sitting, waiting idle for data to transfer in and out of the chips. So from this, what you could see is that these numbers are significant. These are 4 actual benchmark models. And you could spend, in one of them, in M2, we're showing over 50% time in exposed networking. So this is what's so unique about the training cycle times that we have, that the balance is skewed towards network I/O because of the need to access a lot of the embedded tables. This is precisely because of the amount of model parallel comms we do, all-to-all communication, and the extremely high bandwidth that we need between the accelerators. So this is even higher than what you would see in traditional HPC systems. So today, what we see is the need for both very high injection bandwidth and very high bisectional bandwidth. For a little more context, let's recap what comprises an AI training cluster. So first, remember, these DLRMs, or personalization models, are trained on very large amounts of data, which correspond mostly to unstructured and unlabeled interactions from a variety of applications. Typical dataset sizes are on the order of petabytes. So for that, we need distributed storage, which we use the Tectonic file system. We then have the storage and the cache interconnected on a data network, while the compute cluster is interconnected by a high-performance computing fabric. So remember, the bisectional bandwidth is our real challenge. It's what leads to the exposed networking. What I'm showing behind is a dramatization of a future meta training cluster. These training clusters can be up to 4,000 accelerators large, and we believe that in the near future will require up to 1 terabyte per second of compute network per accelerator. This is more than an order of magnitude more growth than compared to today's networks. So beyond the merely increased bandwidth, we need high-performance, non-blocking fabrics with predictable behavior under heavy loads, with modern congestion control. So one of the asks of the community is to focus on open fabrics that are going to be a key to enabling AI at scale. And this is an area where we'd love to partner. Finally, one area of the challenge that's particularly acute and very close to my own heart is the I/O itself. At the bandwidth and scale we're targeting, power is a critical constraint. We have a limited fixed power budget for the data centers or for the clusters. And as you can see, we can see into the future as we move from 200 gigabit per second to 1.2 terabit per second, that the actual power afforded to the network and to the optics is growing relative to the compute. One way that we can address this challenge is to embrace all of the modern technologies across this whole industry on driving optical I/O and co-packaged optics. This could be a step function for the industry. So it's another area that we have to keep our eye on as far as the radar, because what we need to be thinking about is how do we drive lean design practices into the actual systems design, into every single element that we're putting down on a platform, into a data center, and look at the entire interconnected picture to strip out any waste in the system. So with that, the power supply that's needed to move data all around accelerators, around the clusters, CPO is a pretty natural fit. As a community, we continue to make incredibly great strides together to push the envelope on innovation. But we have some really large and important challenges ahead of us. One way to overcome these challenges is to really focus more intently on the hardware-software co-design. It's going to be critical for us to actually break through the next barriers. We also need to come together to solve this bandwidth problem, whether it's memory or network, and balance the loads in the system. And then finally, we can align as a community on liquid cooling strategies for the data center of the future. OCP has an incredibly important role to play in the future systems designs that we take to the open market. It's driving an increased pace of innovation across the board. So we've come an incredibly long way together as one community, and I can't wait to see where we take it next. Thank you.
Please welcome Meta's Open Source Ecosystem Lead and OCP's Incubation Committee Co-Chair, Dharmesh Jani.
There is no army mighty enough to stop the march of an idea whose time has come. Today, I'm going to talk about two such ideas whose time has come. Good morning and welcome, everyone. I'm DJ, and I'm delighted to be here with all of you. So many familiar faces. I'm equally grateful to have this opportunity this morning to be the voice for many of you in the audience who have worked extremely hard to move these ideas forward. Truly, it's a sign of a vibrant and a dynamic community, a thriving community that can take ideas from inception to execution. All of us, as a part of Open Compute Project, is one such community. With over 300 members and growing, we represent the entire value chain of data center industry. Among us, we have silicon vendors, we have system builders, we have solution providers, and we have data center operators. Together, we have contributed over 280 contributions in OCP. We have taken countless journeys together in open, collaborative fashion across many different stakeholders. Journey of sustainability is one such journey, which started roughly around 2 years back when the idea was first proposed to the incubation committee. Few of us got together, and that December, we voted on 14 different ideas. Sustainability was voted number 1, with support from many of you in the audience who voted. And then in 2021, the group came together and started working on this initiative. The group started looking at many different areas, such as circularity, life cycle assessment, carbon emission, metrics and measurements, and even life cycle assessment. They started contributing with a lot of data into the Open Compute project and also socialized across 11 other projects on all the things they were trying to do with sustainability. And these projects themselves took this idea enthusiastically and started working on their own ways. In fact, you heard from Zane at Intel this morning on modularity, which is one such idea which was being pushed for developing circular designs. This enthusiasm, contagious enthusiasm, can be explained from many different perspectives. The perspective which I find simplest, easiest to understand, and resonates with me most is the perspective of data center energy usage. If you look at the data center energy usage over 20 years since OCP was conceived, the growth is phenomenal. We are expecting 15 times the levels of 2010 by end of this decade. The worst case models put it at 40 times. If you look at the share of the data center energy consumed for the global energy, we started at around 1.5%, and we are expected to finish this decade perhaps in double digit. It's phenomenal. Now, the energy growth in data center may not be a surprise to many of us. We are aware of this. Again, we heard in the keynotes this morning. What is interesting to me is that energy actually is a proxy for two aspects. Operational footprint, of course, because that's what we are calculating. But it's also proxy for manufactured equipment. In fact, the equipment has to be manufactured first upstream and then gets deployed downstream and operationalized, and that's where you're measuring the energy. Both of these aspects have impact. Both of these aspects contribute to the greenhouse gas emission and carbon footprint for the data center. Greenhouse gas protocol sets an accounting standard which many of the OCP companies follow to report their carbon footprint and greenhouse gas emission. The greenhouse gas protocol classifies the emissions in 3 categories. Scope 1, which is related to the direct emission. Scope 2, which is related to indirect emission as a result of purchase of the energy. And Scope 3, which is related to the supply chain emission. All these 3 are considered when an organizational footprint is reported. In case of data centers, Scope 2 and Scope 3 are the dominant ones. Manufacturing equipment-related emissions would fall under Scope 3, and data center operations, the energy consumed, would fall under Scope 2. The interesting thing which recent study has found is that when you look at the energy provided by the traditional grid, the Scope 2 dominates as a part of the total emission of a data center. This is not a surprise, actually. It's kind of intuitive and obvious observation. But the interesting thing is when you look at it from the grid with renewables, the bottleneck flips dramatically. Now the Scope 2 emission is reduced substantially because your energy sources are from renewables, and Scope 3 becomes the dominant contributor to the life cycle of data centers. More recent studies have revised these numbers even more. The interesting thing for me is not what the exact number is. What is interesting to me is that there's a flip. You go from Scope 2 as a dominant one to Scope 3 as a dominant one. As I mentioned, we have over 300 members here representing the entire value chain of data center industry. Together, it's our responsibility to address this bottleneck. Many of the OCP leading technology companies have already announced science-based targets to be achieved by the end of this decade, mere 8 years away. How are we going to do that without addressing this bottleneck? We have to put the right structure within OCP, and it's with great pleasure I want to announce that we are now adding sustainability as the 12th project, joining the 11 other projects within OCP. I find an interesting coincidence here. It's a very pleasing coincidence that OCP is in the 12th year of operation, and this is the 12th project joining the list of projects. Now, this gives us a common umbrella to bring all the ideas, expertise, knowledge, exchange to allow us to move forward to address this bottleneck. The second announcement I want to make is around OCP tenets. When OCP started in 2011, it started with 4 tenets we all are very familiar with. Openness is in our core. We work to improve efficiency. We work to have an impact. And we also deliver scalability. Today, we are adding the 5th tenet to the pantheon of the tenet, and sustainability becomes the 5th guiding North Star, which is going to be there for us whenever we are thinking of contributions starting in 2023. Again, a structure determines behavior. Putting these 2 structures is going to help us, guide us in direction to achieve the goals which we want to. So we have taken some journey together. We have gone somewhere. We have arrived at some place. However, the path continues up to higher ground through the clouds, and there's more work to be done. As we say at Meta, the journey is only 1% done. Over the last 2 years, as I talked to many passionate individuals within the community, there were a couple of challenges which actually resonated deeply with me, and I would like to share some of them with you today. I call them big, hairy, audacious goals in front of us. The first, we have to look at embodied carbon in silicon. Silicon powers everything within our data center, whether it's compute, whether it's networking, whether it's storage, or even AI/ML. if we have to understand the carbon footprint of the data center, we must understand the embodied carbon in silicon. Second, I mentioned circularity. The group delivered design for circularity within OCP. Technically, these are very complex challenges to create designs which are circular, which can extend life cycle. But in my opinion, the harder challenge is the business challenge. Trying to find right business models which can push circularity forward is even harder. And this requires, again, all of us within value chain to work together to create these new business models which can index on circularity first. Third, and my favorite, is going beyond PUE. Power usage efficiency has driven our data center designs for the last 10, 12 years. However, I want to share a small story here. Growing up in India in a middle-class family, every time I would leave my room with lights on, fan on, my father would magically appear and yell at me to turn the lights off. And it happened every time. He was always interested in improving the PUE of our household. He didn't care about sustainability. He didn't care about being green. All he cared about was his pocketbook. He just wanted to save money on electricity bill. Efficiency is a common sense. It's part of OCP tenet from day one. We have to go think beyond efficiency. If you have to think of green data centers, you have to bring green measures into your calculations. Like John Doerr said in his famous book, measure what matters. And all three things we have to do with full transparency, because there is data exchange which is required across the value chain players. And we have to look at things collectively, which requires transparency. So what's my call to action as I conclude my remarks here today? First, we are all here together. Please engage and try to learn about all the activities happening on the sustainability side, participate in the project. And the simplest thing you can do is, we have a mixer tomorrow between 11 and 1. Please come join and meet your fellow travelers. Second, contribute with your time, your thoughts, your expertise. Sustainability is such a cross-functional field. It requires everybody's input, and everybody has something to offer. Third, as you learn ideas from here, please take them back into your organization. Talk to your leadership. Talk to your peers. Try to evangelize. Empowering open is the theme of this conference. What does empowering open mean to me? It means we have to be transparent in all our interactions. We have to be open and transparent, and that is something which is important, especially for this topic. And last, and my favorite, is you got to have fun. If you're not having fun, if you're not building new friendships, relationships, then you're not doing it right. So as I wind down here, I've had opportunity to talk to many passionate, thoughtful individuals within this community. They have shared their ideas, their inputs, their thoughts. As I prepared my remarks this morning, I want to thank all of them. And you know who you are, for your time and your inputs. And lastly, I want to thank all of you in this audience for your time and attention. And I wish all of you a phenomenal rest of the Open Compute Summit. Thank you.
Please welcome Ampere's Chief Product Officer, Jeff Wittick.
Good morning. It's great to be here at the OCP Global Summit. You've heard a lot today about sustainability. I think you're going to hear a lot throughout the rest of the day as well. And you've heard about some of the challenges of creating a sustainable data center using legacy technologies. I'm going to talk about how we can use new technologies to actually reduce our data center footprint. It's actually really simple. More compute with less power. And I'm going to talk about how these technologies are being made available today through the Open Compute project. It goes without saying that the cloud has had numerous benefits in all aspects of our lives. Everything from drug discovery, remote work, staying in touch with loved ones. All of these areas have been made possible thanks to the advancements in the cloud. However, as you saw from Dharmesh, the rising energy consumption of the cloud is threatening the ability to continue to grow out the cloud footprint. Today, some hyperscale data centers consume as much as 100 megawatts. That's enough to power 80,000 US homes. In total, data centers consume as much power as some entire countries, such as South Africa. And these numbers are going to continue to grow unless we bring forth new solutions to reduce our footprint. A couple of real-life examples. In West London, housing prices are soaring. There's a crisis. Sounds a little familiar, right, for those here who live in the Bay Area. There have been a number of multi-unit housing projects planned. And when those projects were up for approval, it became evident that data centers that had moved into West London neighborhoods had actually consumed all available power on the grid, and those permits were put on hold until 2035 until additional power could be brought to the grid. So real-life impact to folks in London and the UK. In Dublin, Irish power consumption for data centers has increased by 144% in the 5 years leading up to 2020. And that power consumption is projected to grow to as much as 27% of Irish power by 2029. To put that in perspective, 36% of all households in Ireland are rural. The total power consumption of those households is less than the total power consumed by data centers in the country of Ireland. So as a result, local power operators have delayed many projects in the data center space. They put a de facto moratorium in place until new solutions can be found. Here in the US, in Oregon and Washington on the Columbia River, water consumption, especially in the face of drought conditions, is of growing concern. And many projects have been put on hold until additional solutions can be found. So the list goes on and on. Real impact from increasing data center consumption. Now, everyone here in the room has done amazing work over the last decade or more to make many improvements, which is why we haven't faced a major crisis to date. We've seen major improvements in PUEs as more and more efficient ways of cooling data centers and more efficient power delivery systems have been developed. The consolidation into very, very efficient hyperscale data centers has also allowed for further improvements in sustainability. And data center operators have increasingly invested in and utilized more and more green power. But more needs to be done if we're to avoid the growing crisis in data center power consumption and overall sustainability. The continuing impact of increased power consumption, of water usage, and as Dharmesh mentioned as well, the embodied carbon in all of that equipment and all of those data centers is a major problem. Now, it starts with the CPU itself. If you can deliver a CPU that delivers higher performance and higher capacity with less power, you can solve the problem at its core. It reduces the overall resource strain from a power perspective, from a thermal perspective, and from an equipment perspective. This isn't a fantasy. This isn't 3 to 5 years away. These solutions actually exist today. So instead of building your data centers over the next couple of years, building out more and more compute, and using legacy processors while doubling the power consumption of your data center, if you just switch to Ampere's cloud-native processors, you could reduce your power consumption by 20% and still meet your compute needs. So, just like the data center architecture and software, the hardware itself must be cloud-native. Now, this is similar to the type of transition that happened a couple of decades ago, as the transition from mainframes to a client-server model occurred. First, the usage model changed. Then the software that was surrounding that usage model changed, adapted to become higher performance, more and more efficient. And then finally, the hardware changed as well. We're right in that transition right now. The move to cloud native has obviously happened from an architectural perspective. It's happened from a software perspective. And it's time for a new type of CPU, a cloud native processor, to be adopted in order to drive higher performance and better sustainability. So what's happened in the move to cloud native? Applications have become more and more distributed. They're shared amongst many, many users. Infrastructure is shared amongst many users, many applications. Workloads are scaling out. They're designed to be incredibly portable. They're broken down so that you can gain efficiencies by scaling out. Running one core in the cloud for 100 minutes costs the same amount as running 100 cores for 1 minute. So using that type of parallelism from the workloads themselves, from the architecture itself, you can get amazing efficiency. However, to realize that efficiency from a hardware perspective, you need hardware that's predictable, that is elastic, that's efficient, hardware that delivers consistent performance to all users, that scales up and down based on demand, and that allows you to maximize the amount of compute you have without building more and more data center, more and more equipment. So to do this, cloud-native hardware, cloud-native processors utilize a grounds-up, cloud-first approach to designing the CPU. They shed the baggage of a legacy architecture designed for older use cases, and it really changes the game in terms of sustainability. If we look at what a cloud-native architecture could provide to you, a cloud-native processor could provide to you versus what the legacy architectures are capable of, a cloud-native processor is able to run at nearly 100% utilization without sacrificing performance, without introducing unnecessary or undesirable impact from noisy neighbors. You can scale across 128 or even more cores to maximize your capacity. You can run at the lowest possible power with fully populated racks, not stranding capacity within your rack, not having invested in equipment that isn't fully utilized. And by running at the lowest power, you can reduce your thermal load and reduce the need to utilize complicated solutions that might force you to overhaul your entire data center. So, highly utilized, you have scalable capacity, it's dense, and it's low power. The net result is a quantum leap in efficiency and the maximum performance per rack. So what's this really look like in practice? Here are a couple of examples and the differences that you might see and how this translates into amazing efficiency and sustainability. 3 to 4 times better performance and efficiency. So no compromises. You can have both now, performance and efficiency. Consistent performance in the face of noisy neighbors. So no need for inefficient workarounds in order to preserve performance or security in your data center. Linear scalability, no diminishing returns, scaling all the way up to 128 or more cores. This allows you to run at 100% utilization instead of maybe at 30 to 50% in order to be able to adapt to peak capacity demands. This reduces the need for unnecessary data center buildouts. And the lowest power consumption at all times. By not bumping up against the thermal constraints, we can deliver the highest performance without being pegged to TDP. Again, utilize the thermal solutions that you have today and multiply the impact of future thermal solutions that exist. The net result, no stranded capacity, thousands of additional cores per rack, the highest overall performance per rack for a wide range of cloud workloads like databases, web serving, media encoding, caching. What can you do with this? So either you could deliver 2 or 3 times more performance in your same rack and power envelope, the same footprint, or you could reduce your footprint, reduce your needs from a power consumption, from a water, from an equipment perspective. That's less builds. This opens up the edge as well with previously unattainable levels of performance at low power. We're seeing build-outs from cloud to edge deployments in distributed locations, in vehicles, those that are terrestrial, even those high up in the atmosphere. So this opens up a wide range of possibilities. And we're seeing some of the results today. So HPE has launched their ProLiant RL300 Gen 11 servers based on the Ampere Ultra and Ampere Ultra Max processors. The tagline, more cores, less wattage, predictable performance. That results in the greenest possible solution. So they've really embraced this move to cloud-native computing and the sustainability benefits that it provides. Also, I think really interesting for those in this room, not only does that platform support the traditional HP ILO manageability, but it also supports OpenBMC for all of the open source enthusiasts in here. This makes it easier and easier for cloud providers or enterprise users to take advantage of this type of efficient cloud-native processor technology. Plus, by offering this up in GreenLake, they have a complete solution in the hybrid cloud space as well. So everything from multi-cloud running across many, many clouds to on-prem private cloud to hybrid usages. Cloud Sigma is one of those users. They're seeing amazing benefits. They're able to meet their sustainability goals. They're able to deliver lower costs to their customers. And Scaleway is able to take advantage of the technology from the Ampere Ultra processors by achieving higher and higher performance, which allows them to deliver a more efficient cloud. And it's not just HP. There's a wide range of platforms available today, from Gigabyte, from Inspur, from Supermicro, from WeWin, and the HP platform that I mentioned. And these platforms are taking advantage of open source firmware, OpenBIOS, OpenBMC, and many of them are using the OCP mezzanine card as well. You're going to be able to see these around the summit here over the next couple of days. So now we're at my favorite part. Last year, we contributed the Mount Jade platform for our Ampere Ultra and Ultra Max processors. We contributed the hardware and the firmware to make it easy for people to innovate on top of this cloud-native platform. We have been a contributing member of DCSCM 2.0. We're seeing really, really great momentum with this technology over the last couple of years, especially thanks to the community here within the Open Compute project. This year, I have another exciting announcement to make. So this year, we're contributing back our Mount Mitchell platform to OCP. It's our next generation cloud-native platform. It features DDR5, PCIe Gen 5, and it also features a bunch of the modular technologies that we were hearing about earlier. So this supports the OCP 3.0 NIC, and then also it supports DCSCM 1.0. So these are the first pieces in being able to deliver that modular approach to server designs by bringing the manageability, the security, and the control to a discrete module. And that approach is really important to us. We are also participating in and we're contributing to DC MHS 2.0. As you heard earlier, that type of interoperability is going to lead to faster innovation on disruptive technologies. So really excited about the work that's being done in that space. Also, the firmware, just like last year, the firmware is going to be made available to the community. So you'll be able to take this platform, adopt it, or adapt it to your own needs. Another important area that we're working in is ARM System Ready. ARM System Ready, if you're not familiar with it, it's a program that allows you to test and then certify your platforms to ensure that the operating system and then the surrounding software just runs out of the box. So no worries when deploying the hardware in the data center. And today, we actually have 17 different Ampere platforms that are System Ready SR certified. We also have 3 cloud instances, those from Oracle, from Google, from Microsoft, that are System Ready VE certified. And so we will be bringing the Ampere servers into the OCP ARM System Ready Experience Center. That's going to allow more and more OEMs, ODMs, CSPs to certify their platforms as system ready. It's also going to allow more OCP accepted and OCP inspired platforms to come to market. So really excited about the work that's being done there with the ARM System Ready Experience Center. And lastly, in the future, as a platinum member of Open Compute, Ampere is very dedicated to continue to bring new technologies, whether it's around DCSCM, DCMHS, continuing contributions around open firmware, and continue to drive more and more platforms for an open and a sustainable cloud. So there's lots to demonstrate here. You can see here a number of our partners that have Ampere platforms deployed in their booths, demos, partners that are helping to build a green and a sustainable cloud. So be sure, check out their booths. Also, after the summit, these partners have our technology available firsthand, so you can check that out. You can also check it out in the OCP Experience Center. So as you continue to hear today about a sustainable cloud, just remember, Sustainability starts at the core, and the best way to reduce your core power consumption is with green and sustainable processors with Ampere's cloud-native processors. So thank you, and have a great rest of the summit.
Please welcome Broadcom Senior Vice President and General Manager, Core Switching Group, Ram Valega.
Good morning. Oh, a lot of people are leaving just when I get started. Can I try to convince you guys to come back? By the way, I'd like to thank the OCP team for giving us an opportunity to present here, and also those of you who are still staying in this presentation for the next few minutes. So a couple of things I want to leave you with as you go through this presentation today. One, you've heard from Alex's and the teams that presented before that networking is absolutely essential for computing. Whether that is computing through CPUs or GPUs, you hear everything about HPC, ML, AI, and I can tell you none of this is possible without networking. That's number one. The second thing I'd like to leave you with is nothing does networking like Ethernet. Oftentimes you hear a lot of other technologies, whether it is FIDI, CD, SONET, ATM, dare I say, InfiniBand, but at the end of it, the reality is Ethernet is what it's going to be able to enable large-scale computing, and that's really what I want to leave you with. Okay? To start with, you've heard a lot about even Moore's Law earlier on today, and the basic premise of what's happening on Moore's Law is the following. Every successive process node, the next generation process node, the returns that we are getting are diminishing. When we went from 28 nanometer to 16 nanometer, we probably got a 30% efficiency in power. Now when you go from 16 to 7, and from 7 to 5, you'll be lucky if you get 10 to 15% efficiency in power. But also at the same time, the cost per node in terms of what you're paying per transistor is also going up. So you look at this and say, what the hell is going on, right? As one is the efficiency per node is actually going down. You're paying a higher price. And during all of this period, the size of the die is no larger. So against this background, you look at it and say, OK, how do I deal with more and more compute? The application's asking for more and more compute. And Moore's Law, it's not scaling. What do we do? And if you look at the last 10, 15 years of what's happened in the world of compute, people have said, look, we can't scale up, right? We can't scale up and build mainframes. I hate to say it because we actually sell software that runs on mainframes. And we said, instead, we have to scale out. And the whole idea of a distributed computing took place. As a matter of fact, I think this might be a picture of Google's data centers a long time ago, because you only get their pictures of the data centers way past when they are not using it anymore. But anyway, this kind of picture shows you how they took commodity servers and linked a whole bunch of commodity servers to essentially do very, very large-scale computing. And the extent to which this has happened, without that kind of a distributed computing today, whether it is the service from Meta, the Instagram, or Netflix, or AWS, a lot of this would not have happened. Imagine for a second if you tried to build these kinds of services like using mainframes, IBM would have been very rich, and none of this would have happened, right? So it just doesn't work out. And so really, the way the architectures have evolved is taking smaller pieces and trying to put them together so that you have a very, very large system and being able to do it in what is called a scale-out kind of an architecture. Now, when you do a scale-out architecture, and this is where I do my pitch, which is all of these computes are great, but if you cannot connect them and you cannot make them all work like a single instance, it's not going to work out. And what you need here is the network, right? And actually, Sun said this 30 years ago. Sun Microsystems, they don't exist now. They're a part of Oracle, whatever they are right now. But the reality is, they had the foresight back then to say, the network is the computer. And that's really what it is. You need a network that essentially is able to tie all of these pieces of compute together and make it look like one large system. Now, you say, well, the network is a computer. We buy that concept. So then, what is the network? And this is where I've talked about before, which is if you look at the history of networking over the last 10, 20 years, there have been a lot of technologies along the way. SONET, ATM, FIDI, CD, you name it. And then over a period of time, eventually, Ethernet became the de facto standard. And why is that, right? It's a couple of things. One is it's plug and play. It's an industry standard with the specs which are published. there's a very, very healthy ecosystem of manufacturers who are building, Ethernet switches. Even for us as Broadcom, while we would like to think that we are a leader in, Ethernet switching, there's so much competition we have. And effectively, there is a lot of innovation that happens when it's an open ecosystem. There's a lot of competition, and everybody's kept honest trying to make sure that they are the leaders. So there's a lot that happens here. Now think about the magnitude of 600 million ports for a minute. The world population, give or take, is about 8 billion people. So over the course of 10 years, just over the course of 10 years, the installed base of Ethernet is more than the world's population. Another way to think about it is for every person that's born every year, there's 4 Ethernet ports being produced. That's the scale of Ethernet. So just imagine a kid that's born, you just give them 4 Ethernet ports and say, happy birthday, right? Try that with InfiniBand. Good luck. You'd be paying trillions of dollars in world GDP with InfiniBand. Sorry for anybody who loves InfiniBand here, but I got to take my shots. So then you look at this and say, OK, so this is all awesome. Ethernet was perfect when we were using CPUs. We bought CPUs from a bunch of x86 ARM vendors, so on and so forth. But now when we start looking at GPUs, it is taking this whole concept of distributed computing to the next level, right? Even inside a single chip, you have 1,000 cores. Now think about it. That is complete parallel processing inside these 1,000 cores, like something that's never happened before. Now you take that and say, OK, this is great, but then I want to build an entire data center across multiple racks that is making all of these thousands of cores come together. And then you say, is InfiniBand the technology of the past? Actually, a long time ago, I used to see this T-shirt that said, this Ethernet is not your grandfather's Ethernet anymore, right? Because Ethernet kept evolving, and every time there's a new challenge thrown at it, it comes up and steps up to the challenge. So the same thing is happening again. While compute's going from very serialized tasks to parallel tasks to many cores, and many cores actually being networked together, what's happening is more and more challenges are being thrown at Ethernet. So a couple of things. One, which is historically Ethernet TCP/IP was what we called internet scale. You had this TCP/IP protocol that did all the congestion management, and generally what it was is it would start backing off traffic before there was too much traffic on the network, but then it also caused a lot of delays in your network. If you try to do that on a scale of hundreds of thousands of GPU cores, what will end up happening is you'll really slow down the amount of time it takes to complete a job, right? Imagine going onto a search engine or going onto your Instagram, and it takes forever to load. It's great for my kids because hopefully they'll drop the phone and do something else, but the rest of you won't like it. So you have to make sure the network is not the bottleneck. I think Alex just showed you a slide that said, look, network is a bottleneck. Like, great, network is a bottleneck. That's good for us. We'll produce more networking. Hopefully you guys will buy more. But the issue here is there's some technical issues that have to be solved with Ethernet. And the things that have to be solved is, if you think about it this way, if you're on a highway, and I always say, when the last 5% of the people in the Silicon Valley get laid off, suddenly the road opens up. It's not that the road's double the size. It's the last few people who drive their cars on the road that cause a lot of congestion for everybody else. And that's exactly how the traffic on the network also works. So there's a few things you have to think about, is load balancing, latency, congestion management, and so on and so forth. And all of these are areas that other technologies, what I would call either proprietary technologies, when somebody else would argue, no, they're just single vendor technologies, but nevertheless, some of those other technologies have solved in the past, and Ethernet has not necessarily focused on those, and that is what we're so laser-sharp focused on going forward. So you look at that and say, OK, so here's a slide. Okay, now before I do the build on this slide, you will all say, what the hell is this? Excuse me. What is this showing? Ethernet is in a really bad shape. And what the slide is showing you is the red graph here is the latency when you do a workload using Ethernet as a networking fabric. And on the y-axis is the latency. Latency is the amount of time it takes to complete the job. And generally, when something is higher on the y-axis, you think it's good. But in this particular case, when something is higher on the y-axis, it's actually bad. You want to be lower on the y-axis. And what you see here is the yellow line is InfiniBand, and the red line is Ethernet. And Ethernet has a couple of orders of magnitude slower in performance. Again, a couple of orders of magnitude slower in performance than InfiniBand. So it would make no sense to buy Ethernet, even if InfiniBand costs you 2 orders of magnitude more, right? But over the last few years, a lot of innovation has happened on Ethernet. And now when you actually look at the performance of Ethernet, there is this blue dotted line that is sitting right on top of the yellow line. right? That basically shows you that the performance of Ethernet today, hands down, at a fraction of the price, will give you what you may be thinking of from an InfiniBand standpoint, okay? Now, this is not work that we have published, we and maybe Broadcom or somebody else. This is actually work that is being done at the Los Alamos National Labs, because they're super motivated. They're running a lot of HPC clusters, they're doing a lot of MLAI, and they want to be able to scale it at very large scales. So they did a test of Ethernet with RDMA also on Rocky to see how its performance would be. Now, here's another beautiful thing about Ethernet. Ethernet can actually scale. You're not constrained to doing 256 servers or 512 servers or 1,000 servers. That is usually what other technologies scale to. You can actually build a fabric that is tens of thousands of servers. And this is all kind of commodity Ethernet that you can get from any given day, 5 or 6 vendors, right? And that is what Ethernet is able to do. But this is not sufficient, because we're not stopping at where we are today. There's a lot more problems to be solved. And to talk about some of the innovations that there are to be solved, what I would like to do is invite Professor Mark Handley. He's a professor at University College of London. In the interest of full disclosure, Broadcom just bought his company because he was doing some really cool stuff. And a lot of what he spent over the last couple of decades is working on reducing congestion in the networking fabric. And he actually flew over from London just to do this deck. Yesterday, I told him he had 5 minutes. Today, I told him he has 4 minutes. So I'll let him on before I take more of his time. Welcome.
So Ethernet has come an awful long way. But once you start to build really large-scale data center networks, we still end up with latency problems. And the reason we end up with latency problems is because of the interactions between the traffic patterns, the very heavy workload, especially for AI-type traffic, and the network topology. And when we dive in and try and figure out what's really going on in these kind of networks, we realize that basically there's 3 real problems where we're building queues in the networks and increasing latency. And the first of these is where you've got transient oversubscription typically at the top of rack level, where you've got bursts of traffic and you simply can't get into the rest of the network from the top of rack. The second problem we find is where you've got what we call flow collisions. And these are due to when your flow is routed through the network, the switches are doing equal cost multipath, and they don't perfectly load balance the network. So you get multiple flows collide on the same link. Collisions create congestion. Congestion creates latency. And the third problem we see is that a lot of these workloads have very large incast problems. So you get a big implosion of traffic arriving at a particular receiver. And if we look at the orders of magnitude of the overload these create, the incast one is much worse. We get something like 5 orders of magnitude overload due to incast, whereas the others are usually less than an order of magnitude. So in order to actually get low latency performance out of these large-scale Ethernet networks, we're going to have to actually address how to control these queues, how to avoid building large queues in the network. So first of all, let's look at the incast problem. The incast problem, we've got a lot of people sending to one receiver simultaneously, and this is typical of various workloads like AI. And to be clear, this isn't really a throughput problem. This is a latency problem, partly because the tail latency of those particular flows, and partly because this incast causes latency for other flows too that are not related. So we've been working on solutions for this. And the solution we particularly like is called drop congestion notification, where you drop the payload of the packet and priority forward the header. And this means that the receiver knows completely what's going on. And then after that initial burst of traffic, the receiver can use a credit-based flow control mechanism to clock traffic across the network and to manage that traffic very carefully to the available capacity. The second part of the problem, this issue with flow collisions, that's best handled by doing packet-level ECMP, packet spraying. And if you do that, you can really very evenly load balance your network and basically eliminate the problem of flow collisions. If you don't like packet spraying, and not everybody does, then an alternative is to do cognitive routing, where the switches are looking at the downstream congestion and doing very short timescale rerouting. And the third part of this is, what do we do with this transient oversubscription at the sender? And the only thing you can realistically do there is to keep the packets back in the sending host. And when you detect congestion, that's not a problem. We can easily ramp down. That's very easy to do. The problem is, how do you ramp back up again quickly when that congestion disappears? And a great technology for doing this is in-network telemetry, where we can find out very rapidly that the problem has gone away and it's time to ramp back up. Another piece of this puzzle is also precise congestion notification, where the switches can actually tell the sending host precisely which flows to pause, so that only the ones that are experiencing congestion can actually have a problem. So those are the main pieces I wanted to talk about, these issues to do with transient congestion at the sender, flow collisions, and incast. And we think we have all the solutions for this now to actually build these very large-scale data center networks that scale and have low latency, even under heavy workloads. Back to you, Ram.
Oh, thank you, Mark. We paid a lot for Mark's company. Hope you found the last 3 slides useful. So last year about this time, I had the luxury of actually showing you what I call Tomahawk 4, which is a 25 terabit device, right? Which is 256 ports of 100 gig or 512 ports of 50 gigabit Ethernet. This year, we just got lucky in terms of how the timing worked out, that we have a device that is Tomahawk 5 that is 50 terabits. So essentially, we doubled the bandwidth. And you could think we doubled it in a year, just because I showed it to you last year, and I'm coming back this year with the reality is we're still 18 to 24 months in between. But the one thing that's worth calling out is, in the world of Ethernet, whether it is us or somebody else, this methodical cadence of executing and being able to double the bandwidth is something that you can almost count on, and you should. Because every time we build the silicon, there's a lot of the ecosystem here that spends their effort and their own dollars to be able to put a system together and get ready to go to production. So being able to have a reliable partner that executes on a cadence is extremely important. So, Ethernet just being able to continue to improve the performance while actually doing a lot of innovations around the areas that we just focused on, congestion management and so on and so forth. I can tell you that we are extremely confident, both today in terms of what we are delivering and in terms of what we will be able to deliver going forward, that it will be the networking technology of choice, bar none, for anything related to HPC, MLAI, and any high-performance computing that you need to do. Right? So now that we've done that, what we did do is we actually made the reference design for Tomahawk 5. We contributed that to OCP. And also, some of the innovations that Mark's talked about, the software infrastructure that is needed for it, which is the SCI APIs, those are also some things that we've already contributed to the SCI community. We have to just kind of go through the process of them debating whether or not it meets their needs and any changes they want to make. And once it's all done, you should expect that that will also be available in the community. Right? That said, what I'd like to do is actually introduce Hans from Meta, Hans Jürgen, the Director of Engineering at Meta, to come and actually talk about what they see as challenges that they face in how they're solving the networking needs going forward for a lot of the AI, ML use cases that Alex has touched on. So Hans.
Hello, everybody. Good to see you. So there's a lot to talk about, and you only gave me 2 minutes. So I tried to summarize it. We have a lot going on in Ethernet world, of course. You know the contribution we have made, Wedge 40, Wedge 100, Wedge 400, B and C. We started with 6-pack in the fabric. We have called it then the next generation backpack, mini-pack, and mini-pack 2. Maybe we come up with a new name at some point in time. But fact is that Ethernet is really hard to argue against, and we benefit. And we don't just benefit from a size perspective of the switches. We also benefit from an architectural and solution perspective as we were building fabric aggregators and H-grid. So we actually built much larger switches out of smaller switches, and Ethernet is a technology to scale up and scale out. As we move into the AI HPC world, there are many problems. You indicated some of those, and we're investigating very hard the networking part, the buses, the architecture, and try to optimize the CPU, ASIC accelerator, and network memory bandwidth construct. And to this extent, clearly, we look into technologies that allow us to save power, give us predictable performance, work on tail latency, and for sure need to scale. Power and cost efficiency is key, and also reduction in complexity. The least amount of forwarding plane interactions are key in all of this. To this extent, we, of course, look into things vertically and horizontally. On the hardware level, we look into co-packaged optics, we look into reduction in signal integrity, higher speeds, SerDes, and so on and so forth. And the networking piece plays a key role, and we're investigating, of course, a very predictable performance, also with the technology that Broadcom is providing. To this extent, this is also a call for action. You probably heard me. I just mentioned in 2 sentences probably 10 problem statements. That doesn't make it easy for the community, but still, I think I'm looking forward to collaborating with Broadcom and the industry community on all of these problem statements, and I'm really looking forward to this show. Thank you very much.
Thank you, Hans. So I will just end with what I started with, which is bet on Ethernet. You need networking to be able to scale out. And others have already bet on it. One of the world's largest supercomputer has already been built on Ethernet, and it's actually running over 1.1 exaflop. So that's all I wanted to say. Thank you for your time, and have a good rest of the day.
Please welcome Open Compute Project's Chief Technology Officer, Bijan Norouzi.
Good morning. Hope you guys have had a lot of coffee and eaten a lot of good food, whatever. I won't be long. This is a really quick announcement that we want to make, but to make the announcement, I want to kind of set up how we got there. So these are our tenets, and they're imperatives for our contributors to kind of develop this better idea, right? And so these tenets are measured against every idea and contribution that comes in, which is working pretty well. We have 10 years of success with this. So there's also kind of a flip side to these tenets, right? And if you look at these tenets a different way, it's kind of like an imperative for the foundation team to optimize our processes and how we do things. So use as an optimization tool, as a filter to look at everything that we do. We've come up with a couple of insights, and I'd like to share one of those with you guys today. So here we have kind of like a typical hardware design process where it's hardware and software required for this, whatever it is we're making. And so, it starts the same typical way where hardware guys get together. They start looking into building a specification, a design, whatever it is that they want to do first. Then they start building, okay? They build, they build, they build. You get to a milestone. Once they get to that milestone, there's a shareable piece of hardware. And that shareable piece of hardware is kind of like not finished, but it's the basis of whatever they need to have. So from that point, they keep working. There's technical debt they have to go work. There's feature, finish outs, all kinds of stuff. But they get through this, and at the end, there's a great product. OCP has a lot of great finished things that we've defined, and that part works. The software guys kind of follow the same exact process. The problem with that is that, there's no reinforcement of one thing to the other, and I'll explain that in a second. But I want to kind of give a shout out to somebody, Cliff Grossner, in the foundation team. He's worked really hard on listening to all of the feedback from the community and taking this feedback and listening to kind of what's the important pieces and distilling it for us so it's easy for us to understand, and looking at our strategic positioning for each of our projects in the marketplace and the impact they have, versus the tenants again. And, came up with some, enlightening realizations that were going to be important here. And one thing was, we make fine hardware products or software products, but they don't really reinforce each other. A better piece of hardware isn't because it had fantastic software and vice versa. So there's kind of a hole in our process if we want to get to excellence. So, like I said, we are continuously trying to optimize our processes and continuously trying to do a better job for everyone in the community. So we got busy and looked at what we needed to do. Turns out there is a better way, okay? And this better way is hardware, software, co-design. I've actually heard some other keynotes mention it, so you know it's important. When we take our teams and we blend them together, right? We got a hardware team and a software team working together to build something unified, to build something, you know, that with the end in mind. Magic things happen, right? So here's our process chart, and you'll see that mostly it's the same, right? Hardware guys go build hardware, software guys go build software, but the wonderful thing is they're synchronized, they're coordinated. And when they're coordinated, good things happen. Feedback happens, synergies happen. So that's what we want. We want this. And we've talked about this before as an organization, but you know, it's really difficult to put into practice. So we kind of thought within ourselves, like, what pieces do we have and what pieces are we missing, right? We've got an excellent hardware organization, fantastic community. We've got great software guys, great community. But maybe there's something else that we could search for that we could add to the mix to kind of make this like a breakthrough moment for us. So we talked to our friends at the Linux Foundation. We said, hey, we've got this idea. And they said, you know what? We've got the same idea. And we said, all right, well, here's what we've got. What do you guys got? So you know how things go, right? Silicon Valley, we get to talking, and some really good ideas flow out of it. So, you know, if you think about the fantastic architects and engineers that we have at each community, there's a lot of knowledge. There's a lot of leverage there to build great things, right? So what's different? We have worked with Linux Foundation in the past. We have things like Sonic at Linux Foundation. What's different is our strategy. And this is what I was talking about before. We're thinking about this in a different way. So with that, I'd like to bring some help on the stage here.
All right, thank you, Bijan. Excited to be here. See a lot of familiar faces as well after a long time. For those of you who do not know Linux Foundation, we're the open source software, one of the largest, 800+ projects, including Linux, but Kubernetes, you heard PyTorch, a lot of networking projects like ONAP, Sonic, Dent, you know, you name it, Edge and IoT projects, and a lot more. So we host all of those projects with a very vibrant software community. So that's a quick intro. You also heard all the keynotes talk about hardware, software, co-design. And that's an interesting concept, but it is hard to execute. So let me explain it how we do it and how we see it. If a spec or a specification exists, code it. That's what we do. If it does not exist, code it and upstream it to the specifications organization. Okay, you want the two to be in sync, and you want a very rapid cycle. As Bijan said, right, those diamonds were there for a purpose. That's what co-design is. You bring the communities together. I can guarantee you, having done both hardware and software myself, it is not easy to be the best at both. You can't have the best architect do software and hardware, but when the two combine, it really works out very, very nicely. Okay, so with that said, today we're announcing expanded collaboration. And as we know, networking, Sonic, all of those things were already part of this, but we're going to expand the collaboration between OCP and Linux Foundation to include a lot more projects, including networking, Edge, IoT, as well as the newly announced project Caliptra, right? And we're really excited to working together, collaborating, and pulling together a community of very bright people. And one final thing, if you want to understand more on how the software is designed and architected, Please join us at the next big event called Open Networking and Edge Summit, or One Summit in Seattle, November 14th and 15th. That's where the software community gets together to put these pieces together. Registration's open, so we'll see you all there. And thank you for the partnership.
Looking forward to it. Like I said, this is not just a hardware and software repository, but it's going to be a virtual community. So we're going to get together the virtual community. We're going to wrap our hands around whatever problem that we're trying to solve, use cases or whatever, and we're going to work together. So this is really different for us. First targets have been identified, like you said, and stay tuned. Thank you.
Please welcome Google's Vice President and Engineering Fellow, Partha Ranganathan.
Hello, everyone. It's truly a pleasure to be here. First, let me wear my hat as one of the directors for the Board of Open Compute. Welcome all of you to the summit. It's truly amazing to see so many people here in person, almost record-breaking numbers, and I hope all of you have a fantastic 3 days ahead. So what I'm going to do today is to structure my talk in 3 parts. The first part, I'm going to talk about a bunch of technology trends, and I'm going to try to set up the problem statement and the opportunity that we have. In the second part of the talk, I'm going to talk about how we are at a very interesting era of system design, where we are radically rethinking everything, every layer of the stack, all the way from silicon to software. And then in the last part of the talk, I'm going to talk a little bit about what it means for us as a community. And I'll talk a little bit about some exciting announcements we have in terms of Google's partnership with Open Compute. So when we think about infrastructure at Google, we think in terms of designing the planet-scale computing that powers all the Google services that we all love to use, web search, Gmail, YouTube, even cloud. And for the past 2.5 decades, we have done a fairly good job solving some pretty significant challenges at tremendous scale. How do we get performance, efficiency, resilience, reliability? But more recently, we are starting to see some headwinds. Prior speakers all talked about the slowing of Moore's law, so I'm not going to belabor that too much. But I did want to talk about how the slowing of Moore's law leads to technology platforms across multiple dimensions. So you have the graph on the left that shows traditional slowing of computing, but you can also see how technology plateaus happen in memory cost efficiency, in storage costs, in power efficiency. And in some respects, these challenges could not happen at a worse time. So just as we are seeing all of these slowdown in the supply side, we are seeing some phenomenal increases in the demand side of things. So for example, in machine learning, some estimates from OpenAI suggest that the demand for computing is doubling every 3.5 months. Similarly, cloud computing is a fairly new disruptive technology, and the adoption of cloud computing is exponentially increasing, with businesses spending hundreds of billions of dollars per year on the digital transformation of their businesses. On top of that, we have a few additional challenges that pertain to reliability and security. So on security, most of you have heard about some recent efforts around side channel vulnerabilities, Spectre, Meltdown, Foreshadow, and so on. But what is very interesting is that the fix to these security problems often involves some pretty significant performance trade-offs. Similarly, Zane talked about reliability in his keynote as well. What we are finding is that the slowing of technology scaling leads to increased silicon falls, silent data corruptions, and once again, the fix to all of this involves some pretty significant performance trade-offs. So this combination, where on one hand we have some significant headwinds on the supply side, new challenges in security, new challenges in reliability. On the other hand, we have some phenomenal, unprecedented increases in compute demand. That is the problem statement that we are all looking at. So now the good news is, as a community, we have been looking at this problem for a while, and we have made some pretty phenomenal innovations. We have been rethinking every level of the stack from mud to cloud. We are rethinking new silicon custom accelerators. We are rethinking hardware infrastructure and data center infrastructure. We are rethinking the software stack all the way to distributed systems and cloud computing. And so if you start with what are we doing in custom silicon, we have evolved from going beyond traditional CPUs and GPUs to more custom ASICs that are targeted at specific workloads. So the TPU, the tensor processing unit, optimized for machine learning workloads. The VCU, the video coding unit, optimized for video acceleration. The recently announced IPU, the infrastructure processing unit for smart networking. And the good news is we are just about starting here, and there's tons of opportunities for more new accelerator designs, more innovation in this space, including my favorite, which is about thinking about more fine-grained, closely coupled accelerators for core data center libraries and functions. On the hardware side, server design, as we know it, has traditionally, for the past 5 decades, been fairly straightforward. But the server of the future is going to look fundamentally different. It's going to have modularity. It's going to be disaggregated. There's going to be a lot of heterogeneity and diversity in the fleet. We are going to be software-defined, namely, we are going to wrap the hardware in layer of software and expose that as the service. And we are going to be focusing on all the abilities I talked about, security, reliability, availability, and so on. Similarly, at the data center side, we are going to see some pretty fundamental changes. Once again, we are going to see a modular design. But we are also going to see us embrace an emphasis on manufacturing, an emphasis on automation, again, an emphasis on software-defined infrastructure, but also a focus on environmental sustainability or green computing. Popping up a layer of the stack, when we look at distributed systems, again, we are at a very pivotal moment. If you think about prior inflection points in distributed systems, whether it is the birth of the internet or client-server or scale-out systems, we are at yet another inflection point where we are rethinking a new epoch of distributed systems, one that is based on low-latency networking, optimizing for microseconds, one that is thinking about new programming models for accelerators, one that is thinking about abstracting compute and storage as a service and presenting it to our customers. And finally, on top of all of this, cloud represents, again, a generational disruption in terms of how we think about our system design. Beyond democratizing access to computing, cloud computing has been focused on delivering completely new capabilities in terms of how businesses store, use, understand data in their journey on digital transformation of their businesses, and we are at a very, very nascent stage of this particular journey. So what does all of this mean? Individually, any one of these changes that I talked about is a fairly significant disruption. But when you combine them all together, and you go beyond just design innovations to thinking about innovations in deployment and velocity. So how do we do fast product launches? How do we build hardware ASICs much faster than we have ever done? And when you combine all of this, I believe we are truly at a pivotal moment in systems design. A once-in-a-generation, a career-defining moment where we will all look back and say, hey, we got a chance to do this. Now, when I talk about this new era of systems, this new excitement that I have around that, it is not going to be possible if we don't have a corresponding emphasis on innovation in open industry ecosystems as well. Google is obviously no stranger to open source contributions. We have played a leadership role in fostering several open source systems, whether it is Kubernetes, you just heard from Linux Foundation, Android, Chrome, TensorFlow, a lot more. And what we have found is that contributions to open source can be multidimensional. We can start off with standardizing industry standards and increasing the adoption for the entire community to do. Or we can think in terms of growing the ecosystem, make specific contributions to the community, support through engineering resources, through cloud resources. Or we can provide broad leadership, either at the policy level or at the board level, or share best practices, opensource.google.com or something of that kind. And so today, on behalf of Google, I'm very pleased to continue this rich tradition of collaboration with open source ecosystems with a very strong partnership with Open Compute on more open hardware ecosystems as well. Over the next 3 days, you'll see more than 40 different talks where you will see Google participation, leadership, collaboration with a broad set of industry partners, where we'll be making a whole bunch of different announcements. And I want to focus on 3 big areas where I'm very excited about: server design, trust and reliability, as well as sustainable computing. So our first contribution is around the area of server design. I already briefly talked about how the server of the future is going to be very different than what we have seen in the past. And so if you think about all the changes I talked about, whether it's around accelerators or disaggregation, all of that comes with significant complexity. You no longer have a plug-and-play model that works anymore. And so at this summit, tomorrow at the Future Technology Symposium, we will be presenting Google's vision of what we call a multi-brain server for the future. And if you want a sneak preview, you can also go to the Google Tech Expo talk today at 1:20 p.m. And in these talks, we will share how we are working with the broad open compute community to collaborate on all the individual components that together make this vision a reality. How do we innovate in modeling and out-of-band management? Things like Redfish, OpenBMC. How do we innovate in modularity? You heard about Zane talking about Google's collaboration on DCMHS. How do we work on industry standards, NVMe, CXL, and so on? But also, how do we innovate on additional new components that are needed, arenas, composability, and so on? Our second contribution continues to invest in the area of reliable and secure computing. Can we go back one slide, please? Ooh, OK, OK, apparently our third contribution. So our third contribution goes into the area of trusted and secure computing, going beyond discrete root of trust to new edge cases, new confidential computing use cases. And so today, along with other industry leaders, AMD, Microsoft, and NVIDIA, we are pleased to contribute Caliptra, which contributes a reusable IP block for chip-level attestation at the package and the SoC level. And so the Caliptra spec is already available for all of us to look at, and code is coming shortly as well, so that we as a community can work together to make sure that we harden the IP block in this very important area. OK, can you go back to the previous slide now, please? So our third contribution is in the space of reliable computing. And you already heard from Intel about how silent data corruptions are a pretty significant problem. And this can be a very insidious issue when we think about deployment at scale in the fleet. How do we kind of avoid software toil for our developers? How do we make sure we have avoid unintended consequences like cascading failures and so on? So once again, today, we are very happy to work with a spectrum of different industry partners to announce a new open compute server component resilience workstream, where we'll be focusing on 3 major kinds of contributions. As a community, we're going to be discussing and publishing metrics so that we can consistently track this important area. We are also going to be looking at test execution frameworks and suites that we can all use to identify and resolve these problems. But we are also going to be looking at test environments that can provide access to faulty devices across both industry and academia, so that we can encourage more research to take a full systems approach to solving some of these problems. So the final contribution I want to highlight today is around sustainable computing. So you've already heard this theme throughout all the prior talks as well. And Google, again, has been a leader in sustainability. We were the first to go carbon neutral in 2007, 100% renewable energy in 2014. And we have a very audacious commitment to go net zero emissions across our entire value chain by 2030. And it's not just within Google. As the cleanest cloud in the industry, we've also helped share these best practices with our customers, whether it is new carbon reporting for cloud customers like Twitter, or enable customers like Etsy to have dramatic energy savings. So today at Open Compute, we are extremely delighted to strongly support open compute in sustainability as the fifth tenet. And we intend to contribute on multiple dimensions. We are hoping to initiate and lead the conversation around industry standards and come up with important metrics in the space. But we are also looking forward to contributing our best practices, whether it is some of the phenomenal work we have done around carbon-aware scheduling, or some of the optimizations we have done to reduce Scope 1, Scope 2, and Scope 3 emissions. So I want to conclude with basically leaving you with two top-level messages. Number one, we are at a fundamental inflection point in defining a new era of systems. Every level of the stack, from silicon to hardware to data center to distributed systems to cloud computing to velocity, is being reinvented. It is a very, very exciting journey, one that we are all going to look forward to. And this journey will not be possible without equally vibrant, open industry ecosystems. Google is extremely pleased to collaborate with Open Compute on this journey, and I hope all of you can also join us in this journey as well. Thank you for your time, and enjoy the rest of your conference.
Please welcome Microsoft's General Manager, Cloud AI and Advanced Systems Engineering, Zaid Khan.
Good morning, everyone. I hope everyone is enjoying the summit so far. It's so wonderful to be back on stage at this year's OCP Summit and see such a fantastic audience. When it comes to building the Microsoft Cloud, our work to standardize design for systems, board, racks, and other parts of the data center infrastructure is paramount to facilitating forward progress and innovation across the computing industry. We joined Open Compute Foundation back in 2014 and have since then made a number of contributions from rack and server architecture, the Sonic network operating system, security, liquid immersion, and many others. Our belief is that by working with the open compute system ecosystem, we can bring standardization, consistency, and interoperability to Azure customers. Our goal with such innovations, collaboration, and contribution is to ensure we are providing Azure customers an environment where they are operating reliable applications in the most trusted cloud, and that we are powering sustainable transformation. We are now entering a new era of transformation in the cloud. It is an era where security is not just about securing a server, storage, device, or network. It is an era we are calling confidential compute, where we, as a trusted cloud provider, enable securing our customers' data while processing it. This means that we have to enable our customers to be the only ones that hold their keys to their data, processing this data in such a way in hardware-based trusted environment where even administrators or someone with physical access cannot see it unencrypted. Microsoft Azure is a leader in cloud security and privacy, offering a broad range of confidential computing services to help organizations run their many workloads and keep businesses and customer data private and advance levels of security. As the demand for confidential computing grows from cloud to edge, so do the requirements for consistency and transparency of many security mechanisms that protect all the various workloads. With the rise of edge computing, the resultant growth in the exposed attack surface also presents a need for stronger physical security solutions. In this context, there is an increased need for greater transparency in the infrastructure that underpins these technologies and upholds hardware security promises. Now, as we step forward in this new era of confidential compute, there's an imminent need for building a root of trust into silicon, and it is a journey that requires deep collaboration. As my esteemed colleague earlier, Partha, announced, today we are jointly announcing Caliptra, an open source silicon root of trust that produces cryptographic proofs around the hardware protections in place for confidential workloads. Designed with security experts and industry leaders in confidential computing across AMD, Google, Microsoft, and NVIDIA, Caliptra is a forward-looking approach casting greater transparency into hardware security. I will now invite Brian Kelly, partner architect at Microsoft and one of the key architects of Caliptra, to talk you through this joint contribution in a bit more detail.
Good morning, Zaid. Thank you. Good morning. I hope you're having a wonderful summit. I'm going to talk a little bit about Caliptra. So Caliptra is an open source root of trust in the form of a reusable silicon block designed for ease of integration into SoCs. Caliptra provides transparency and consistency of the root of trust. The root of trust is an important element in secure devices. The root of trust provides a set of foundational security properties that underpins higher level security features. This foundation gives workloads integrity assurances of the hardware underneath. At its core, the Caliptra root of trust takes cryptographic measurements of an SoC security state. These measurements, along with Caliptra's endorsement, can be used to verify the trustworthiness of an SoC. Security leaders from AMD, Google, Microsoft, and NVIDIA have come together to form Caliptra and provide transparency and consistency of the root of trust. Aligned on the vision that transparency builds towards stronger security and consistency creates a healthier ecosystem that the industry can benefit from. We're open sourcing Caliptra and invite the community to get involved and help build a more secure future. So Caliptra has 3 key components. The first are the specifications describing Caliptra's architecture and Caliptra's integration into secure devices. The second is the RTL that composes Caliptra and forms the reusable block that can be synthesized into SoCs. And the third component is the firmware that runs on Caliptra. It's written entirely in Rust. It gets measured by Caliptra's hardware and forms part of Caliptra's identity. Now, Caliptra transcends hardware and software. And to bring those communities together, the Open Compute and CHIPS Alliance have come together to support Caliptra. And as such, the specifications that describe Caliptra's architecture are being made available through Open Compute. The RTL and the firmware that composes Caliptra is being set up in CHIPS Alliance. Caliptra is another example of how Open Compute and the Linux Foundation are working to serve communities across the vertical integration of hardware and software. For more information on Caliptra, you can scan the QR code and come see our talk on Thursday in the security track. There will be demos in the expo hall of Caliptra at the Microsoft booth. You can also reach out to members of the Caliptra team at AMD, Google, Microsoft, or NVIDIA. And with that, I want to thank you all. I hope you have a wonderful summit, and I'm going to hand you back to Zaid. Thank you very much.
Thank you very much, man. Thank you very much, Brian. Now, to continue expanding on our theme today on confidential compute for our customers, we are introducing today Hydra. Hydra. What is Hydra? Hydra is a new baseboard management controller in partnership with Nuvoton. A BMC, as we all know, is a diagnostic and recovery controller which has special privileged hardware interfaces for acquiring debug data and telemetry from CPUs and GPUs. These interfaces present security concerns as they are targets for attacks that bypass conventional security defenses. As threat models evolve to restrict admins with physical access to hardware, the BMC needs security properties to establish secure links to an external root of trust. Microsoft collaborated with Nuvoton to design a new security-focused BMC with enhanced hardware security throughout the BMC SoC. The silicon-integrated root of trust supports identity flows with hardware engines for fast cryptographic operations and hardware-managed keys. The root of trust has a one-way bridge for activity monitoring and controlling the BMC security configuration, including which internal security peripherals the BMC can access. This unique feature allows the fine-grained BMC interface authorization, enabling various scenarios where temporary access to a debug interface can be granted to the BMC only after it attests its trustworthiness. Hydra has fully open-sourced firmware running OpenBMC, the Cerberus root of trust, and integrates TPM functionality. Another demo that you're welcome to see at our booth later on today. Now, as we step our foot deeper into confidential compute, seems like that's a common theme we're having today, we are discovering that a standard hardware security module such as TPM is susceptible to an attack. A discrete TPM is a chip typically used to protect secrets for the software running on various CPUs and conditionally released based on the CPU's boot measurements. Historically, the bus between the CPU and TPM is susceptible to an attack from physical adversaries wishing to falsify attested measurements or obtain TPM-bound secrets. In our approach to multi-layered security across our data centers, infrastructure, and operations, we believe in defense in depth, and that all interconnects should be cryptographically secured from from interposer-based type attacks. In partnership with Google, Infineon, and Intel, we are announcing today Project Kirkland at OCP. Project Kirkland demonstrates how using firmware-only updates to the TPM stack and CPU root of trust, the interconnect between the TPU and the CPU, TPM and CPU, sorry, can be secured in a way that prevents substitution attacks, interposing, and eavesdropping. We are open sourcing this methodology and plan to standardize this approach while working with other TPM manufacturers to adopt the same methodology so that these techniques become available to all. Now let's shift gears to a bit on scaling infrastructure. We have been observing a unique shift in the world of AI and high-performance compute. There are a number of accelerator-based solutions that you've heard of today even for AI, video codecs, and various other types of accelerators. But all these various solutions are built as commonly as separate discrete systems. When these systems are deployed at scale inside data centers, they become super complex to manage and costly to maintain. What is interesting about these accelerator cards is that they have so much commonality. When we looked at these common aspects, such as form factor, power, and management interfaces, we realized that there's a need for a converged design that brings these form factor, power, and management interfaces into a flexible modular design. So today, we announce our contribution of Mount Shasta, a modular chassis that enables multiple accelerators to fit into a single chassis supporting 48-volt power feed. And we designed this in partnership with our friends at Quanta and Molex. Mount Shasta is designed to be fully compatible with OpenRack v3, which you heard about earlier today, with a modular form factor that provides support for high-power devices and hot swappable modules with flexibility in changing module-to-module connectivity. Mount Shasta also supports additional flexibility by connecting external host chassis, and you're welcome to see this in the demo booth today after this keynote. The first virtual I/O virtualization specification was called Single Root I/O Virtualization, or SRIOV. It was released probably more than a decade ago, and conceived for the virtualized environment of that time. Generally, fewer than like 20 virtualized workloads per server, right? Pretty small compared to what we do now. SRIOV loaded sort of all of this into virtualization and management logic into PCI devices. We just increased device complexity and reduced the I/O management flexibility of the virtualization stack. So over time, CPU counts grew, virtualization stacks matured, and container and microservices technology exponentially increased workload density. As we transition now from enterprise scale virtualized environment to hyperscale virtualization, it's clear that I/O virtualization must evolve as well. In cloud environments, I/O devices, including network adapters, GPUs, and storage controllers, are shared among many virtualized workloads requiring their services. Now, hardware-assisted I/O virtualization technologies enable efficient routing of I/O traffic from these workloads through the virtualization software stack to the devices. It helps keep overhead low and performance really close to the bare metal speeds. Earlier this year, we collaborated with Intel and contributed SIOV specification to OCP that will enable device and platform manufacturers access to an industry standard for hyperscale virtualization of PCIe Express and Compute Express link devices in cloud. This enables more sort of scalable, efficient, and cost-effective hardware designs for data centers. Now, to conclude, I would like to say that Microsoft continues to believe that collaboration through open source community engagement and industry partnership makes technology advancement more rigorous, faster, and just better for the world. We are looking forward to the continued partnership to enable innovation, scalability, efficiency, and sustainability for the data center infrastructures of the future. And please visit our booths and various engineering workshops. We have multiple talks, exact talks, and learn about our contributions. Feel free to talk to anyone, and I really hope to see you all there. Thank you, everyone.
Please welcome Samsung's Executive Vice President, Sang-Yen Cho.
What a day. I'm pleased to be here with you, giving the last keynote of the day. My name is Sang-Yen Cho. I'm part of the team that builds Samsung SSDs that store your precious data. I join you today at a pivotal moment for our industry, the dawn of a future that will revolutionize our society. We have a name for that future: the age of data. From AI and IoT to the metaverse and autonomous cars, so many of the applications that will change our way of life will also produce humongous data. Just how much data are we talking about? According to the IDC, 33 zettabytes of digital data was generated in 2018. How much will it be in 2025, 3 years from now? Current estimates put the total at around 175 zettabytes, and that's a tremendous amount of data by any measure. However, all that data comes with a cost. The more data we create, the more power and carbon footprint is needed for data centers and to produce more semiconductors. With that, I'd like to address the fundamental question that matters most to our industry today. Is all this sustainable? Sustainability is a global issue, one that we must address together through open collaboration. open, together, collaboration. The moment you hear those three words, you understand just how important they are. You can find them throughout the OCP's mission and vision. Samsung shares the OCP's collaborative values, and we welcome its decision to make sustainability core to its mission. And so, with all of us gathered here today, let's examine how we can create a more sustainable future for data centers from two perspectives: products and manufacturing. Before we discuss the product side of the equation, allow me to provide a brief overview of our efforts to advance open source innovation. Samsung has been pioneering open source technologies for many years. That includes F2FS, the file system that powers all the Android smartphones, as well as multi-stream and OpenMPDK. We first joined OCP back in 2015 and became a platinum member earlier this year. 2 years ago at the OCP Summit, we made waves across the industry by unveiling an open source reference storage platform called the Poseidon Project. Today, I'm thrilled to announce that, as promised, together with our partner Inspur, we have completed our contribution of the Poseidon V1 specification to the OCP community. This follows our successful release of the Poseidon OS on GitHub. We look forward to contributing our Poseidon V2 spec in 2023. Today, our commitment to innovation is as strong as ever, especially when it comes to SSDs. Our products have been adopted by data centers and system vendors around the world. We've been developing the world's best OCP-compliant SSDs ever since NVMe SSD specifications became a focus of the OCP storage project. And they've quickly become hyperscalers' most widely adopted OCP-inspired products. To me, this not only proves the effectiveness of the OCP technologies, but also shows the true power of open source collaboration. Best of all, as these products become more widely available, they will help create a more sustainable cycle. Now, I would like to take a moment to talk about the team that makes this all possible: Samsung Memory's Global Open Source Team, or GHOST. GHOST includes more than 100 engineers from various sites who have undertaken numerous projects since 2020. Our ultimate goal is to improve the open storage and memory ecosystems. Our team is heavily involved in Linux kernel and QEMU, as well as libraries such as XNVMe and tools like FIO. Efforts like these will be vital to building a sustainable ecosystem for future data centers. Achieving that goal will require even more innovative memory technologies. Technologies like Smart SSD 2.0, Memory Semantic SSD, and memory expanders. Set to roll out in 2023, Smart SSD 2.0 is a computational storage product with a built-in data accelerator. It allows you to cut processing time by more than half, improve host CPU utilization, and reduce energy consumption by as much as 70%. This makes it an effective next-generation memory product in terms of both energy and resource efficiency. The memory semantic SSD that we are developing is based on the CXL interface. It will add efficiency to the accelerators, memory, and storage devices used with CPUs in high-performance computing systems. This will allow our product to offer up to 20 times better random read and write speeds than regular SSDs. Technologies like these enable vast improvements for data centers. And when you factor in the huge capacity gains that come with memory expanders, the future of data centers looks even more efficient. We look forward to using these technologies to enable better data center system performance and data processing. Speaking of efficiency, the data centers of the future will need to better utilize space. We can optimize space by filling storage boxes with ultra-high capacity SSDs. That's where petabyte SSD comes in. With their high reliability and a design that can be easily scaled up to create multi-petabyte racks, petabyte SSD can serve as disaggregated building blocks for exabyte-class storage clusters. They are designed to maximize power and density efficiency, allowing us to better utilize server system space and minimize energy use. Please feel free to explore these and other next-generation technologies in our booth. So far, we have examined how Samsung products are helping to realize the sustainable data center of the future. But what about the other side of the coin, manufacturing?
The beginning of sustainability for all. Now, our technology is aimed at the Earth, humanity, and a sustainable future for all. We developed high-performance, low-energy semiconductors with our innovative technology and received carbon footprints certified by Carbon Trust for reducing carbon emissions in all semiconductor manufacturing processes. We are constantly working towards reducing greenhouse gas emission by enhancing the efficiency of gas processing facilities and increasing the usage of renewable energy. Our efforts continue to be recognized by various global organizations by reducing not just carbon emission, but water usage and waste emission as well. All of our semiconductor facilities have received Carbon Trust Triple Standard certification. Moreover, Samsung Semiconductor's independently developed CEPI provides guidelines and initiates environmental management in the semiconductor industry, thus strengthening our position as the industry leader. Samsung Semiconductor has a strong open partnership with various partner companies to foster a healthy semiconductor ecosystem.
Ultimately, everything from silicon to data centers and even data processing can benefit from going green. Samsung continues to promote sustainability in all aspects of its operation. But more efforts are needed. Together, as an industry, we need to think beyond simply developing and releasing eco-conscious products. We must focus on ways to make the entire product journey more innovative and sustainable. But how do we do that? Where do we start? We start with manufacturing. This aspect of operation is becoming more challenging for many industries, including ours. This is because carbon emissions from manufacturing are, frankly, inevitable. To make it more sustainable, Samsung utilizes a regenerative catalytic system, or RCS, to effectively reduce processed gas and pollutant emissions. Samsung was the first in the industry to adopt this type of large-capacity rooftop gas treatment facility. Today, we remain the only manufacturer to utilize this technology. We have also steadily expanded our use of renewable energy over the years to the point that our global sites now run on 100% renewable energy. At the same time, we have been successful in our recycling of landfill waste. As of 2020, all our sites in Korea and China have received platinum certifications from Underwriters Laboratories for recycling 100% of landfill waste. By 2025, we plan to make all our global sites including the one in Austin, Texas, platinum certified. We are also taking steps to address water usage by continuously improving our production process and expanding our recycling systems. We will reduce, reuse, and recycle more water. I'm proud to say that these collective efforts have led us to become the first in the industry to receive the Carbon Trust's triple standard certification. But we are not stopping there. We are taking our sustainability mission further every year. By 2030, we will recycle 99.9% of site waste and keep water withdrawal at 2021 levels. By 2040, we will reduce the amount of air and water pollutants discharged from manufacturing to reach natural levels. And by 2050, we will officially reach net zero carbon emissions. Achieving these goals will not only strengthen our eco-conscious efforts, it will also change how we manage the entire product life cycle, from the meticulous selection of materials to production and waste disposal. This is how we will develop technology that makes technology sustainable. Thank you. Like the OCP, we believe that our industry requires more accurate and relevant sustainability assessments, just like how we did with KPMG. As you can see here on the slide, our Semiconductor Environmental Performance Index, or SEPI for short, evaluates companies' environmental efforts and achievements across 4 key categories with 32 indicators. The SEPI can serve as a clear guideline for this industry. As I wrap up this session, I am reminded once again of our word of the day here at the OCP Summit: collaboration. The path to growing our industry and realizing the promise of the data center of the future lies in working together. That is what I ask of all who are here and share the OCP's collaborative spirit. I ask you to work together to achieve our common goal of ensuring a sustainable future for data centers in a data-driven world. Let's start creating that brighter future together. Thank you.
Please welcome Open Compute Project's Community Director, Michael Schill.
Wow. Thank you all so much for being here today. This is shaping up to be our largest OCP Global Summit yet, and we're so grateful that all of you have taken the time to attend. I hope you caught that, time. I'd like to spend a moment and talk about that word. Our OCP community is as great and vibrant as it is today, due in large part to a ton of volunteers who give freely of their time and their expertise in order to drive the mission and vision of the Open Compute Project forward. If you are an incubation committee rep, a project lead, a sub-project lead, or a work stream lead, please stand up and be recognized. It's awesome. Thank you, David. All right. The OCP Foundation would like to spend just a few moments to recognize 5 individuals who have gone above and beyond in 2022. Anjanea Chagam, Open System Firmware. DJ Johnny, who you heard from earlier today, IC co-chair. Donald Mitchell, project co-lead of the Cooling Environments Project. And John Stewie, server project co-lead. Last but definitely not least, Steve Mills, the incubation committee rep for the Cooling Environments Project. Please give these folks a round of applause. Gentlemen, if you'll just join me, by the stage after we close. We'd like to get a picture and give you your awards. Now, the moment you guys have all been waiting for, we can finally kick off the 2022 OCP Global Summit. The expo hall is now open, and lunch will be served in about 20 minutes. Thank you all for being here, and let's have a great time.